Everyone, my name is Marcela Chauvet, and I'm the director of the RCEA, Rimini Centre for Economic Analysis, which now has its headquarters in the US. Claudio Moran is the director of RCEA in Europe. RCEA organizes several conferences, workshops, webinars a year. We have 14 active research groups, which are listed on the website. We invite you to have a look at www.rca.world. And these research groups also organize several events and activities as well. Today, we welcome the RCEA conference, Recent Developments in Economics, Econometrics, and Finance, which is organized by the RCEA with the support of the Department of Economics of the University of Cyprus, the Tax Administration Research Center, TARC, and the Foundation of Economic and Industrial Research, IOBE. The conference will be for 3 days. We have a large number of very interesting presentations across several fields. I'd like to announce that the revenue of the conference will be directed to finance part of the medical treatment for our friend Miltos Makris, who is a professor of economics at the University of Essex, UK. Miltos is specialized in microeconomic theory and public economics. His numerous contributions include publication in the Journal of Political Economy, the International Economic Review, the Journal of Economic Theory, Journal of International Economics, among several others. Miltos is receiving treatment for an aggressive brain tumor, and all the revenue from the conference will be directed to finance part of his treatment. A separate fundraiser is also being organized by Alessandro Pavan, one of our plenary speakers for the same cause. We are looking forward to the beginning of the conference, so I'll pass the word now to Yanis Valix, who is going to introduce the conference and the speaker.
Hello, everyone. So I would like to mention a few things before I pass the floor to Herakles. So the first thing that I would like to say is a big thank you to all institutions, and in particular to the organizers of this event. I'm sure that you're all aware that apart from the scientific aspect of this meeting conference, the meeting serves a specific purpose. And at this point, I would like to grasp the opportunity to wish Miltos all the best in his fight, and to wish him a speedy recovery. So I would like now to welcome Professor Polemarchakis, who is going to give the first plenary talk. So Herakles doesn't need any special introduction. Anyone, in particular, those who are working on economic theory or on foundational issues which are related to economic policy, they must have a cross with some of his contributions. His research line is wide and covers several aspects. In general equilibrium theory, at least the one that I'm familiar with, general equilibrium theory in complete markets, the identification of preferences, monetary policy, and more recently on sovereign debt. So I don't want to spend time. I would like to give Herakles opportunity to present his work. He's going to speak today about rational dialogues. So, Herakles, the floor is yours. You do have, according to the schedule, something like 45 to, but since we are quick in the introduction, you have 50 minutes for your talk. Thank you very much.
Thank you, Yanni. I want to, in my turn, to thank the organizers for this wonderful initiative. They called us together to talk economics for 3 long days, but also for a specific purpose, a special purpose, which is to say a collective, loud, get well soon to Miltos. So get well soon, and we miss you. Come back soon to talk economics and enjoy what you enjoy and do so well. So I'm going to share screen now, and I am not going to use. I'm not going to use slides, but I'm going to write. So let's see. Let's hope this works.
Herakles, just a clarification. Those who have questions, they can send it to me in the private chat, and I will pass those questions to Herakles at the end of his talk.
Right, hold on, Yanni. If it's for you to direct this, but if there are questions that are for a particular point, let people interrupt. I mean, I don't mind.
Okay, very good. Very good. Very good.
I have plenty. 50 minutes is plenty of time. So I decided to talk about dialogues or rational dialogues, and it may surprise some. This doesn't sound like economics, but the link will be clear, probably is clear to most already, and it will be clear during the talk. Now, talking about dialogues, let's start just with the concept, the word. We would tend to identify dialogues as a literary form with Plato. Now, Plato indeed was and is the definitive use of dialogues in order to convey philosophical arguments. But interestingly, dialogues did not first appear in Plato. They appeared more than 1,000 years before Plato in Sumerian texts. That's the first known record of dialogues. And interestingly, they were used in legal arguments, and in particular, arguments about divorce settlements. So divorce settlements were the first appearance of dialogues on record. And of course, as I repeat, Plato was the definitive use, and it continued. It didn't stop with Plato. Let's just mention Hume's dialogues concerning natural religion. It's a form which has been used and is being used, again, in order to develop philosophical or other arguments. Now, what do I have to say about dialogues? I take my cue from a paper that was written by Aumann in the late 70s or early 80s, and whose title was "We Cannot Agree to Disagree," was Aumann's paper. Now, Aumann, in his paper, had a very provocative and sort of mystifying claim. He made the claim that two rational people cannot agree to disagree. Now, in what context did Aumann make this point? Aumann considered two individuals who start with the same, two Bayesian individuals, who begin with the same prior. So if people start off with different priors, Aumann said nothing, and I'm going to say nothing. It's a challenging, it's an interesting topic that I will not touch upon. So we start with identical priors. Nevertheless, these people, these two individuals, have different information partitions. So as uncertainty realizes, they receive different bits of information. Now, it's clear that if they receive different bits of information, compatible with the information structures and the same prior, they're more than likely to have differing beliefs. Now, Aumann says that if these two individuals, if the disagreement, Aumann would say, that arises, if their beliefs at the end of the day are common knowledge, that everyone realizes what the other's beliefs are, but he also realizes, or she realizes, what the beliefs of the other individual are about her beliefs or his beliefs. If all of this double thinking of any level holds, then this is compatible. This is a situation of common knowledge, and it is compatible only with agreement about the event in question. So, what am I going to? So Aumann, interestingly, made this as an equilibrium condition for those I guess there are many of us in this group. I know I was about to say room, but room in the virtual sense of the word. When we teach, we use Edgeworth boxes. We tell students what happens in an Edgeworth box at equilibrium. But if a student asks, which they often do, well, what happens if prices are not equilibrium prices? We say that we don't say anything. We don't know. We simply look at equilibrium prices. We may give some unconvincing argument about convergence to equilibrium, which we don't very much believe in. But we characterize equilibrium situations. So Aumann went out of his way to describe this, to talk about, to make his point in what he called in the equivalent of an equilibrium framework, that is, to prove the statement, if beliefs are common knowledge, then they must coincide. Now, and if anybody asked, how do beliefs get to be common knowledge, or are beliefs common knowledge, Aumann would say, I didn't say anything about that. All I'm saying that if they are common knowledge, they will be the same. This argument mystified many people, as I said. The argument turns out to be, it's a spark of genius to choose the framework. But in that framework, it is clear, Aumann's is extremely simple, the argument, and I will show it. And I'll show it in a framework which makes a simplified, I'll show it in the context of an example. Now, it is true that the example has a special feature which makes the argument particularly easy and transparent, but this simplification, I shall point out what it is not essential. So the real argument, the one that works in the general case, is equally simple. Now, as I said, so let's see Aumann's argument. And so what is Aumann's argument? Aumann's argument, consider a situation where, and that's the simplifying example that I'm going to use. Suppose you have a state space, which is this. This is a state space. And individual information partitions are rows or columns. Okay. Now, in that space, there is a state of the world that will realize, let's call it omega, is the state that realizes, and there is an event let's call this event A. Now, so this is the setup. There is a prior on this space that I'm not, for the sake of exposition, you might as well think of the prior as Lebesgue call it, or areas, okay, on the screen. So, and both individuals agree on this prior. Now, as I said, there are two individuals. There is individual one, whose information partition consists of rows, and individual two, whose information partition consists of columns. Okay, now, so what happens? Omega, in this context, with many Greek-speaking people, I'll be excused for confusing omegas and W's. To me, they look the same, so, and I think I'm not the only one in the audience. The audience must have the same problem. So I'll never distinguish between the two. I'll just, if I say omega or W is the same thing. So the state omega star realizes. So if individual one observes rows, he is informed of this row, and individual two is informed of this column. Okay. Now, how are the individuals going to form posterior beliefs? Well, the individual one his posterior belief, what is the probability? So the question they ask is, what is the probability that the state omega lies in A? So individual, in this case, we see that it doesn't, but that's irrelevant. The individuals in the picture don't know this. So the individual one will simply take this area, and let's make the drawing not to run into trouble later on. I'll draw it a bit larger. So I'm yet to figure out how to get rid of this problem. Okay. So the set A So that's the set A whose probability we're interested in. So individual one will clearly take the area of A. His posterior belief will be the hashed area over the area of his information set, which is the area of this line, of this row. Individual two will take, I should use a different color. I'll use the same, but I'll do them as horizontal. Okay, so this is for individual two. And now these are things that I have talked about in talks for a long time. It will be later on that you'll see the things that I have to add, which have not appeared in the literature, or at least that I have written yet. So this is the setup. Now it's clear what I said, that these two areas need not be the same. So if these individuals receive their information and they are asked, what do you think the probability is that A has occurred? By A has occurred, we mean W star is in A. The answers will be the two probabilities, which are the relative areas of the area line in A of their information set to the total area. Now, what did Aumann say? Aumann made the following statement. If these are common knowledge, if these beliefs are common knowledge, that is, individual one says Q1. Again, this area over the area of the row. Individual two says Q2, which is this area over the area of the column. Now, Aumann's claim was if Q1 and Q2 are common knowledge, then Q1 is equal to Q2. Now, I don't want to go here into the formal definition of common knowledge in terms of meets and joints and the like of the partitions, but look at this picture, and what is Aumann saying? Aumann is saying the individuals receive different bits of information. One is told of the first column, the other is told of the first, sorry, the last column or the last row, okay, respectively. Now, they also know, and that's important, the blue part, you see that's the framework within which we are working, is of course known by the two individuals. If that's the case, if you know the blue structure, you know the information that your interlocutor will receive, and you know the information you receive, okay? You also know that the prior, your prior and your interlocutor's prior are common. When you hear your individual two, and you hear individual one say Q1, you are going to start thinking, what must this other person have seen in order to say what they say? The other person does the same. And there are also higher levels of thinking, which is to say that my interlocutor heard what I said, and having heard what I said, he maintains his belief. And you can take this, the interlocutor observed what I say, and I observed what he thought all of this higher order thinking, okay, takes place. And yet Q1 is equal to Q2. Then Naumann says Q1 must equal Q2. And in this picture, it is clear, because what does that say? It says that, okay, what is the situation where the announcement by individual 1 of Q1 and the announcement by individual 2 of Q2 do not lead either 1 or 2 to a revision of their beliefs. It should be clear, and if you think about it, you see it is clear, that this is the case if the answer would have been the same. Individual 1 set Q1 on this row, but the individual 2 can also compute what he would have said had he seen row 2, the row before the last. So the computation must yield a result, which is that the answer would have been Q1 no matter what row had realized. You see, a priori, individual 1 is informed of this information set, okay? Observe, and that's special to this picture, that's why I'm saying the argument is simpler, but leave this aside. This information set, the information set of individual 1, intersects all the information sets of the other individual. So simply by seeing his information set, individual 1 has no idea of what the other individual has been informed of. Nevertheless, when he hears the answer, when he listens to the answer, he can make the computation and say, what would the answer have been had my interlocutor been observed of this information set? What would it have been here, and what would it have been here? And he can similarly, individual 2 listens to this, individual 1 listens to what the column responses would have been, and this should have been Q2, 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 okay? So all the rows give Q1. Yes, mistake. So a situation where the beliefs are common knowledge is a situation where every column would give the answer Q2 and every row would give the answer Q1. And Aumann's conclusion is simply a simple algebraic fact that if the Q1s are all the same and all the Q2s are all the same, then Q1 must equal Q2, okay? So this is Aumann's result. And I think that's a clear presentation of it, modulo the simplification of the structure where every information set of every individual intersects every information set of the other. But okay, this makes the exposition much simpler. Now, the mystery that I still don't know how to answer, I must say that I've spoken to Aumann and he's never addressed that issue. I think he dismisses it as not interesting. That's my impression, but anyway. The question is, what happens if you start with the situation, as I said, if you draw a picture at random, neither all the Q1s will be equal, nor all the Q2s will be equal. And that's a situation where Aumann would say, well, I didn't say anything about that. All I'm telling you is that if all the Q1s are the same and all the Q2s are the same, then Q1 must equal Q2. And he would resist any attempt to raise the question of what happens if in step 1, not all the Q1s are equal or not all the Q2s are equal. Okay. And then John Giannakopoulos, with whom I first started working on this ages ago, and I tried actually in an attempt to understand Aumann's paper, we did the following. We said, well, what you do is let's try the simplest thing. You take this picture, you start with this is the picture again. Now, one agent says Q1. That's W star. And the other agent says Q2. Now, what's the next step? The next step is for individual 1 to say, let me compute what Q2 would have been here, 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 and here I know it's Q2. And then what do? I look at all the checks, and let's make a double check if the computation gives me Q2, and let's put an X if it does not, and let's put a double check here. And then what do? I, as individual 1, will say, I did not observe the column, but from the answer of my friend facing me, I know, I can deduce that what he observed was not on this column. Okay. And individual 2 will do something similar. He may eliminate this row, okay? And now what do we have? We have, instead, they can eliminate 1 row, 2 rows, they can eliminate many rows, but we'll have a reduced matrix of smaller dimension in which we can now do the, let's call it the Aumann computation again. It's a smaller matrix, okay? Let's say this. And then I can compute again what the information would be, sorry, what the beliefs would be. Yeah. And let's call these beliefs Q 1, 1, sorry. Let me write it more carefully. Okay. Q 1, 1, and for this and for this will be Q 2, 1, if this was 0, Q1. Now, and then you repeat the process until the process will stop at some point, because at every step you eliminate at least 1 row or one column, and the end of the story is a smaller matrix, let's say maybe like this, okay? With a property which will have the Aumann property, namely the individual who observes columns will say the same, and this individual, so, and here we are back at Aumann. I.e. Q1n and Q2n, and the two Q1 and Q2 equal. So there seems to be a simple elementary argument that Aumann's agreement result not only holds, that is, if the beliefs are common knowledge, they must be the same, but also there is associated with it a very straightforward dynamic argument. Even using the term dynamic glorifies a simple finite adjustment process. It's where we end up with agreement, we end up with common knowledge and agreement. Okay. So this is where things were for a long time, and I thought that this framework now is a natural framework, and this occurred to me. I thought of this long time after we had done the work with John. I think that the first time I presented was a long time ago, but in a conference organized by Miltos and the Department of Economics at Southampton in 5 or 6, maybe 7 years ago. Now, what was the question? The question is this. This adjustment process that I described has generated a dialogue. There is, in period 1, there is individual 1 who talks. Then in period 2, there is period individual 2 who talks. Then in period 3 is individual 2 again. So I'm doing the, you understand, here individuals talk sequentially. Now here, let me make an aside and say that there is an interesting, maybe cultural difference that arises in trying to formulate. That's what I call the dialogue, okay? Because individuals listen to each other, they revise their beliefs, and they continue, and the dialogue that ends when nothing remains to be said. Or indeed, if we have reached an Aumann situation. Now, what is interesting about it's almost at the level of a joke. There are 2 ways to formulate this dialogue, to think of this dialogue, or to formally to define it. You can say that in step 1, both people talk simultaneously. One says Q1, the other says Q2. Both listen to what the other person said, and then they simultaneously announce Q1, 1 and Q2, 1. That's one way. The other way is to say that person 1 talks and says Q1, then person 2 talks, so the sequential versus the simultaneous. Now, this makes no difference in terms of the end result. And I always thought of it as inconsequential, which one do we prefer? But I did some work, or I spoke about this problem for the last 2 or 3 years with a group of people. Actually, their work, I was not part of this paper, but I talked to them a lot. There is a paper written by Alfredo Di Tiglio from Milan, and then Dov Samet and Ehud Lehrer from Israel. And to them, especially the Israelis, I should say, and there they were, that's what I thought was funny. To them, the natural way to define a dialogue is a simultaneous one. Everybody talks at the same time. To people, when you go further north and west that you go, the natural way to formulate a dialogue for people is the sequential one. So I'll do the sequential because I think it's cleaner. The other one is more symmetric, but it's closer to the idea of a dialogue to do it sequentially as opposed to simultaneous. Simultaneous gives a little bit the impression of discussions on Greek or I suppose Israeli television. Now, so that's what the dialogue is. And then the question that I wanted to ask is, if I give you an arbitrary sequence, so given an arbitrary sequence of probabilities, Q1, Q2, Qn, finite, is this a rational dialogue? What does that mean? Can you think of a framework? By a framework, I mean an information structure and a state that occurs that would generate this dialogue. The answer to this question is yes. And I shall explain in a minute how you prove it, or a special case of it anyway. So the answer is that any sequence that you write, realize that the sequence need not have any any monotonicity. I mean, it can be going up, it can be going down. The sequence can be of this form. Okay? It can go. Okay? It can go up and down. There is no way. I am imposing no restrictions on the Qs. All I'm saying is that it stops at some point. No matter how badly behaved the sequence is, you can rationalize it as a Bayesian, what I call a Bayesian dialogue. Now, why is this bothersome? It is in some sense, it is bothersome, or I leave it to you to see to tell me if it's bothersome or not. In the sense that whether you have two individuals who are talking nonsense, who are blabbering, who are just saying numbers off the top of their head, only at some point they get tired and they stop, as opposed to two super rational individuals who behave like the purest of the pure Bayesians, and they share a common prior, you cannot, and if you only have a transcript of the dialogue, you cannot tell anything. You don't know if these people are, as I said, fools or rational Bayesian individuals. I thought it was an interesting result, and that's the result that I had proved a long time ago on about this problem. Now, there is a question, which is what happens at infinity? What happens?
Herakles, just to let you know that you have 11 minutes, okay?
Yes, that's fine.
Okay.
So what happens if the dialogue goes on forever? Okay, and then for this part, and for the simultaneous dialogue, I must say, there is a result by Di Tiglio, Lehrer, and Summit, which says the result extends if a strong, and I shall not go into the details of this because this is just math, a strong convergence condition is satisfied. So there are no finite restrictions, but there is a convergence condition if you want the dialogue to extend to infinity. I have proved the same result for the sequential case. And it's true, a similar result. And I shall give you now, in the little time that's remaining, I shall give you an idea of how the proof goes. Let's think of the case of a monologue. Actually, it was Ehud Lehrer who pointed out to me that this is also an interesting problem. Okay, so here is the situation. Think of this, and I think if you see this picture, you'll see exactly how the construction goes. So here is the state space, and let's divide it into cells, the same as I did in the case before, but it's only one line. Okay. Now, let's suppose that I have two. With each cell, I will associate two numbers. This will be the number A1, A2, A N, A terminal N. Okay? And of course, these are the conditional probabilities of the event A conditional on this information cell. And of course, there are the prior probabilities that we assign to the cell. P terminal N. Okay. Now, this structure will generate a monologue, which is what? We start out, and then the individual, what is Q1? The individual is asked, what is the probability of the event A? And you simply take the sum of AN, so of PN AN. So the initial belief of the individual is the sum from 1 to n of A1, so of Pn AN. Of course, the P's are probabilities, they add up to 1. Then, what do? We tell the individual that A1, cell 1, did not occur. And then, of course, the belief of the individual will be Q2 will equal to the sum from 2 to n of Pn AN, of course, divided by the sum from 2 to n of the Pn. So you understand that doing this, I'm going to generate a monologue which will stop at Qn, which will be simply An. Now, somebody comes and says, okay, this information structure generates the monologue Q1, Q2, Qn. Can you extend it to a dialogue that goes on for n+1 periods? And furthermore, the next announcement is Qn+1, which is given. And you do it as follows. You take this information structure and you say, don't touch anything except for the last cell. And replace this with 2 cells with what property? With the property that here I put An+1, this total length is Pn, and I choose a number. What do I choose? I choose 2 numbers. I choose the number, the probability of this and this that must add up to Pn, and I choose this number A prime n. And what properties do I need? I need the fact that if I condition on this event, the posterior probability would be An. So when you reach here, and there is only this event left, you say An, which is what you said before. When you reach at the end, you say An+1, so you reach this okay, now, the thing is that this can be done, okay, and you can, so this says that you don't touch the argument at the beginning, you only, in some sense, divide the last cell into 2, and this process can go on forever. And what is the result? So the finite argument is, in some sense, the same as before. But now what you observe is that if you want to go this to go on forever, it must be that the weight you assume, the weight you assign to the last probability, okay, which you divide into Pn and Pn+1, you don't want the Pn+1 to tend to 0, okay? Because then at the end of time, you will be conditioning on a 0 probability event. And this restriction, that at the end of time, if you don't condition on a 0 probability event, is the restriction which says that this can be done if the beliefs of individuals, the Qs, converge in a particularly strong way. So if the Qs converge, you can do this construction, and the Pn, so the conditional probability of the last information cell will not be converging to 0. Okay, so an infinite dialogue an infinite dialogue can be rationalized as long as there is a convergence condition satisfied. And now, how do we go? This was true for monologues. How do we do it for a dialogue? Well, for a dialogue, you see, what is important about this construction is that it has a modular form. That is, you have a dialogue here that makes sense. You have a dialogue here which in isolation makes sense, and you take in some sense the concatenation of the two, and that gives you a dialogue that's one period longer. And when you do exactly the same thing, when you have the dialogue situation as opposed to a monologue, but then what we do is that instead of adding individual information cells, we add entire. If we start with this dialogue, if we start with this picture, okay, and you want to extend it to one more period, we don't add one cell, but we add an entire row of cells, exactly the same way that here I added one individual cell. And by exactly the same construction as here, you get the result for an infinite dialogue as opposed to monologue. So there is the very important result of Lehrer, Ditilio, and Summit for simultaneous dialogues. There is a result for the sequential. What is interesting is that the sequential, unlike the simultaneous, one interesting thing about the simultaneous case of Lehrer and Summit and Ditilio is that what the conditions of convergence that you need for a monologue are the exact analog of the conditions that you need for the dialogue, precisely because it's sequential. They require a much stronger condition because they want people to be able to talk at the same time. So I'll stop here and see if there are any questions. Thank you. And again, get well soon to Miltos. Thank you very much.
Thank you very much, Herakles. So we still have 5 minutes for people who wants to raise questions. I see there is no question in the chat, so you can pose the question directly, verbally.
Okay.
Yes, Engel. Yeah. Unmute yourself and ask the question, please.
Okay. Hello. Yes, I'm afraid I cannot make the video work. Sorry. So, I mean, the question is I think it's an obvious one, but intriguing to me, which is that it seems that in the dialogues, people only express their first order beliefs. So why that? Why to stop in at describing their first order beliefs and not talking about the full hierarchy of beliefs? Is this a trivial extension, or is there anything that we can learn from a more comprehensive dialogue?
I did think of it. It's a very clever point. I mean, then every statement would be itself a dialogue. No? Because
yes.
If I tell you my beliefs, I think there will be more information there for sure.
Yes. Mm-hmm.
It's a very good point. Yeah, there will be more information. If people say, don't only say what they think, they also say what they think the other person thinks.
Exactly.
Yes, that's true. That's true. I haven't thought of that, but that's a very good point.
Okay, thanks.
Sure.